S-Chan presents educational video lectures as per the AICTE curriculum. Difficult concepts made easy. Study anywhere, anytime.
In this video, we are discussing some of the periodic properties. So, in the previous video, we have discussed different properties like how the orbital energies are varying between s, p, d and orbitals. What is effective nuclear charge? What is the electronic configuration? How you can write the electronic configuration? In this particular video, we are going ahead and discussing more periodic properties like what are the atomic and ionic sizes, ionization energy, electron affinity and so on. Hello everyone, welcome to S-Chan Academy. Myself Dr. Garima Gaba, and if you want to read more about this topic, then you can refer to the book by S-Chan Publishing. The link of the ebook is given in the description box below. So in today's video, we are going to discuss these topics: atomic and ionic sizes, ionization energy, electron affinity, electronegativity, and the last one, polarizability. So in the first part, we are going to discuss first three parts, that is atomic and ionic sizes, ionization energy and electron affinity. And in the second part, we are going to discuss electronegativity and polarizability, very important topic for periodic properties. So what we consider is, as a social active people, what we do when some guests are coming at our place, then they usually bring gifts or some sweets for us as a token of gratitude or respect. And when they go out or when we see of them, then we give some gifts or sweets to them. So what is this? That whenever someone is coming, they bring something for us, and when someone is going, then we give something to them. So this is the similar concept with our two important periodic properties, ionization energy and electron affinity. In ionization energy, we are providing some energy because electron is moving from the system, and electron affinity, when electron is entering in our system, it brings energy to us. So all these two properties is very important, but before going into this topic, we'll start with atomic and ionic sizes because it affects what would be the ionization energy and electron affinity would be differing between various periodic table. So let's start with first topic, atomic size. As you all know about from the topic itself, atomic radius or atomic size is the distance from the nucleus of an atom to its boundary of electron clouds. So electron, the position of electron is not fixed. It depends on the probability of finding electron. So my nucleus is positive species, and which is having because of the proton, and electrons are in different orbital. So whatever be the distance between the electron to the farthest electron from the nucleus, that will define our atomic size or atomic radius. In other words, it is the distance from the nucleus to the farthest electron that belongs to that atom. So what it would be the farthest electron, we consider the distance of that from the nucleus, and that defines our atomic size. In general, the atomic radius decreases as we move from left to right in a period, and it increases when we go down a group. So what is the periodic trend over here? Okay, so atomic radius decreases and when we move from left to right in a period, and it increases when we go down the group. So let's discuss first trend, that it decreases when we move from left to right in a period. We have seen the periodic table, long form of periodic table. When we are moving from left to right in the period, it says the atomic radius decreases, right? Atomic size or atomic radius decreases. Why it decreases? Because when we are moving from left to right, the N or your principal shell is same. Whether it is second or third period, the shell is same, but electrons are entering in the same shell. So our nucleus is able to attract those electrons in a better way. If the attraction between the proton and the electrons is high, so it will be able to attract those electrons in a better way, and in that case the size will decrease. So when we move from left to right, when we are adding electrons or your elements are entering in this way in the periodic table, the size decreases. And the second thing, it increases when we go down the group. So that means when we are coming down the group from top to bottom, the atomic size increases. The atomic size increases. Why it increases? Because now electrons are entering into the next orbital. First it was in the second, then it is coming in the third orbital, like that. So it is coming in different orbitals, 2, 3, 4. Now whole orbital is getting added into that proper atom. So now that orbital will increase your atomic size in that case. So for your periodic trend for atomic size, it should be important that atomic radius decreases when we move from left to right in a periodic table, and it increases when we move top to bottom in a group. Atomic number increases within the same period while moving from left to right. So as I've told you, when we are moving from left to right, atomic number is getting increased, and it increases the effective nuclear charge because proton is also getting entry into the nucleus. The increase in the attractive force reduces the atomic radius of element. Because of this attractive force between the proton which is getting added and between the electron which is added in the next element, so the attraction is there, effective nuclear charge increases and the atomic radius decreases when we are moving from left to right in the periodic table. So this is very important trend of all periodic properties of different elements. Next thing is ionic size. Similar with the ionic size, ionic radius is the radius of an atom ions. Now you know that the whole species has to be neutral. The ions does not exist as as a single moiety. So ions cannot exist alone. If it is positively charged ion, it will react with negatively charged ion to form a stable neutral complex. So positive charged species are known as cation, and negative charged species are known as anions. Fine. So positive charged species, cation and anions, they combine to form a compound or something which will be giving a neutral compound. So this compound is called ionic compounds. So because it is made from the ionic component, that is cation and anions, an ionic compound is composed of cation and anions. Cation is smaller in size because a cation is formed by removing one or more electrons from an atom. This is also very important property. How it is possible? So cation is smaller in size because a cation is formed by removing one or more electrons. So we can see over here, we can explain this like this. When you are having neutral, so however number of electrons, for example 3 protons are there and 3 electrons are there, because in the neutral species number of protons has to be same as that of number of electrons. But when electron is removed, that means now protons are same, 3 positive, but now 1 electron is removed, 2 electrons are there. That's why this species is a cation. Right? We specify this as a positively charged species because now number of protons are more than that number of electrons. Protons are 3, we have taken example, electrons are 2. Now the effective nuclear charge increases. Effective nuclear charge we have already discussed in the first part of the video. The effective nuclear charge, that means these electrons will have stronger force of attraction from these 3 plus protons. Now in that case the size will get decreased because attractive forces is getting increased, effective nuclear charge is getting increased. So in that case the size gets decreases. So cation is always smaller in size than the neutral atom. If I'll talk about the case from sodium neutral and sodium cation. So sodium cation is always having the less ionic size as compared to sodium neutral atom. Similarly, my anion is always large because now in this case your electrons are more, because now the protons, less number of protons are there which will not be able to attract the higher amount of electrons. Let's see the similar example. For example, now in the case of my anion, these were having 3 positive and 3 negative, that means 3 protons and 3 electrons. Now I am having 3 protons and 4 electrons. 1 electron is more than that of proton, so it is my anion, that is negatively charged species. So in this case the positive charge is having less, it is having less number of protons, so they won't be able to attract the more number of electrons, so effective nuclear charge gets decreases. That is the reason the size of anion is always large than that of the neutral. Although sodium cation is not possible. For example, if I consider my halogen, this is F and this is my fluoride, F minus. So this would always be having higher in ionic radius, or the anion would always be large, because it has extra electrons that are repelled by the nucleus, resulting in the increase of the distance between the nucleus and farthest electron of the electron cloud. So we have to remember, cation is always smaller than the neutral atom and anion is always larger than the neutral atom. Let's move ahead. So ionic size, as you can see, the size of ion is governed not only by its electronic structure but also by its charge, whether it is having +1, +2 and +3, so on. So this relationship evident by the following, this having the ionic radii, like ions having H-, lithium plus, beryllium 2+, these are having electronic configuration same as that of helium, right? All have the same 1s2 electronic configuration. Helium is having 1s2 electronic configuration. Hydrogen is 1s1, but we have added one more electron because it is an anion. So it is having 1s2. Again, lithium is having 1s2, 2s1 as a neutral species. But because it is a cation, so it is again having the configuration of 1s2. Similarly with beryllium 2+. Now, how the size decreases? This size is showing, the radius is showing in the form of picometer. So this is having 154, 93, 60 and 31. So we have discussed my anion always has to be larger as compared to my neutral species, and cations are always smaller in size because effective nuclear charge increases in the case of cation. Since in the case of lithium and beryllium, effective nuclear charge is more as compared to helium, so the size is less because now nucleus is able to attract these electrons in a better way. With the case of H-, size gets increases as compared to helium. Reason, because now it is having, hydrogen is having only one proton, but it is having 2 electrons. So one proton is not sufficient to attract 2 electrons. So the size gets increases. Okay, next property, very important property, ionization energy. So ionization energy, as you know, the energy required to remove the most loosely bound electron from an isolated gaseous atom is known as ionization energy. So from the gaseous atom, if we want to remove the electron, then that energy which we are providing to that system is known as ionization energy. So we have discussed in the last video how these systems are having the increasing energy. For example, if we are giving, these are our levels, like this is ground state, this is excited state, this is having the lowest energy, then this is having the higher energy. If we want to move our electron from the lowest to higher orbital, then we have to provide some energy, right? So whenever a system is getting some energy, the electrons are moving from the lower orbital to higher orbital. But if we provide them some extra energy, so maybe the electron gets sufficient energy so that it can remove the orbital of that particular atom and it can remove the system. That is what it is all about. My nucleus is having positively charged, the loosely bound electron, because it is having the higher energy. So the higher energy orbital that is having the loosely bound electron in the gaseous state, which is very important, in the gaseous state it has to be, when we provide energy to this electron and that energy should be sufficient to remove it from the system, this electron will get removed and will get the simple positively charged species, and this energy which we are providing to the system is known as ionization energy. It is also sometimes referred to as ionization potential and is usually an endothermic process. Since we are giving some energy, we are providing energy to the system, so that process is known as endothermic. It is measured either in the units of electron volts or kilojoules per mole. So this is the unit of energy which we are going to provide, how much kilojoule of energy is required, how much electron volt of energy is required per mole to the system. Among the chemical elements of any period, removal of an electron is hardest for the noble gas and easiest for the alkali metals. So noble gas configuration, as you all know, is the most stable configuration. Whole orbital is filled over there. Now when the system is stable, it is very difficult to hamper it, or you cannot change it. Now it is having the whole orbital is filled, so it is difficult for us to remove the electron. That means we have to give very high energy so that we can ionize that molecule. And alkali metals, because as you know, alkali metals configuration is NS1. N can be anything 1, 2, 3 and so on. So alkali metals are having only one electron in the s orbital. So when we'll remove this electron, then it will attain the noble gas configuration, which would be more stable. this is having, the orbital is having only one electron. So if that electron is also removed, then it will be attaining the stable configuration. That's why the energy required for removing of this electron, or the ionization energy for alkali metal, is less as compared to all the other elements. Let's see ahead. So what are the factors that influence the ionization energy? These 4 factors are there. Size of the atom, we have already, that's why we have discussed atomic radius and ionic radius before discussing the ionization energy, because we know that atomic size and the ionic sizes affect the ionization energy values. So this is very important factor. Size of the atom has to be considered. Charge on the nucleus, whatever would be the charge of nucleus, because that would, those number of protons are attracting the number of electrons, that will affect the ionization energy we have to provide to the system. Third, how effectively the inner electron shell screen the nuclear charge. In the first video, we have already discussed the screening effect or shielding effect, that whether electrons are coming in s orbital, p orbital, d orbital, that factor also has to be considered, which electron we are removing from the system, whether that is an s electron, p, d, and so on. Type of electrons involved, again, what would be the type of electron which we are considering for the ionization energy. So let's see this. Sodium ion forms sodium ions, which we have already discussed. Alkali metal having the configuration of NS1. So it is very easy for us to remove that electron. Very low ionization energy is required. Magnesium is having the configuration as NS2. So it is also very easy for us to remove these electrons. Similarly, aluminium is having configuration as NS2, NP1. So these 3 electrons can be easily removed, not as much easily as we can remove sodium and magnesium, but compared to all other elements, we can easily form the aluminium 3+. That's why aluminium 3+ compounds are known to us in nature. So let's see different ionization energy. First ionization energy, when we are removing one electron from the neutral species, that is your first ionization energy. When we are removing 2 electrons, or what would be the case, we are having the cation and we are removing another electron from that cation, so that would be second ionization energy. And similarly, you can find out third, fourth, and so on. So these are consecutive ionization energy. So we should be knowing why only sodium plus ions are possible and we don't find any compound which are having configuration as Na2+. Why it is not possible? So we can consider the ionization energy. For example, if we want, like aluminium 3+ is possible, but sodium 2+ or sodium 3+ is not found in nature. What is the reason? First ionization energy is what? Sodium ion in the gaseous state, we provide some energy, that is our ionization energy, and we get sodium ion, that is a cation. Second ionization energy, we remove one more electron from sodium plus and we get sodium 2+. We remove one more electron from sodium 2+ and we get sodium 3+. So the energies are first ionization energy, second ionization energy, third ionization energy. So if we want to have the molecules which are having Na3+ or Na2+, we have to get the higher energies. We have to provide higher energies to the system. So the energy required to form a Na3+ ion in the gas phase is the sum of first, second, and third ionization energy of the element. So we have to consider all the ionization energy first, second, and third, and we have to add that energy. We have to provide that energy to the system. Then only we will be able to get the Na3+ or Na2+ ion in the system. Let's see the value so you get the better idea. So this is our value. For example, this is the case of sodium, magnesium, aluminium. First ionization energy when we are having Na+, right? Second ionization energy when we are adding Na2+. So please have a look over here so you can find out. This is 495 and this is almost 10 times greater energy we have to provide. Reason, sodium is having 3s1 configuration. When we remove one orbital from it, it would be having 2s2 2p6 configuration. So the outer electron is removed, the amount of energy which we have to provide is comparatively less. Now it is the most stable configuration, noble gas configuration. In this case, if we have to remove electron from this stable configuration, a very high amount of energy is required. That means 10 times greater than the first ionization energy. Then only we will get the configuration as 2s2 2p5. Similarly, with the third ionization energy and fourth ionization energies always increases. Reason, for example, my sodium or any one having 10 protons and it is the neutral species is having 10 electron. We removed 1 electron and we get over here as 9 electron. Now these 10 protons will have higher effective nuclear charge for these 9 electrons, so they will attract these electrons in a better way. They will not allow any energy to get these electrons removed from the system. Now for the second ionization energy, we want more electrons to be removed from the system. So these 8 electrons, when we are providing second ionization energy. So this is very difficult because now the number of protons are increasing than the number of electrons. So now it is getting more and more difficult for us and more and higher energies has to be provided to the system. So always fourth energy, ionization energy is higher than that of third in every case. Similarly, third is higher than second and so on. And similarly, if you see the case of magnesium, for magnesium 2, it is having configuration as 3s2. So these 2 electrons are able to remove in a better way because now over here we will be having the stable gas, noble gas configuration. But again for the third ionization energy, the value increased drastically because now we have to remove electron from the very stable configuration. So this is how you can find out the value of ionization energy and you will get the idea how much energy is required so that electron can be easily removed from the system. Let's move ahead and move to the topic ionization energy trends in the periodic table. We have seen the trend with the atomic size, like when we move from left to right, the atomic size or atomic radius decreases, right? And when we move from top to bottom in a group, atomic radius increases because whole new shell is being added. Now atomic radius decreases, that means now protons are attracting these electrons in a better way. So it is very difficult for us to remove that electron. So ionization energy increases. Whenever it is difficult for the electrons to get removed from the system, we have to provide extra energy to the system so that it can be removed. So ionization energy of electron increases with the atomic number of the atom and decreases for higher energy orbital. If we look at the periodic table and move from left to right, ionization energy increases due to decreasing atomic radius. So atomic radius was decreasing, so my ionization energy will increase when we move from left to right in a period. When we are moving from left to right, it is having the inverse relationship. Atomic radius decreases, protons are attracting those electrons in a better way. Now I have to provide more energies, more and more energies so that electron can be removed. Whereas if we move from top to bottom, the ionization energy decreases. Now atomic radius is increasing because whole new shell is being added when we are moving from top to down in a group. So now my ionization energy increases. So it is having the inverse relationship, left to right, atomic radius decreases, ionization energy increases. From top to bottom, atomic radius increases, ionization energy decreases. Ionization energy decreases. That means now I have to provide, because electrons are moving far and far from the nucleus, so the effective nuclear charge is decreasing. So now even if I provide very less amount of energy to the system, because electrons is very far from the nucleus, so it will be easily removed. This is mainly due to the presence of more electron shell in the element as we move down the group. Additionally, the electrons are placed at a greater distance from the attractive force of nucleus, as we have already discussed. So now we will be discussing the next property, electron affinity. It is opposite of that of ionization energy. In ionization, what we were doing is we are removing the electron and we are providing some energy. In electron affinity, electron is coming into the system and in that process energy is liberated. Not in all the cases, in first electron affinity. So electron affinity is the amount of energy liberated when an electron is added to the neutral atom to form a negatively charged species. In ionization energy, we were removing electron and we were getting cation, but in electron affinity, electron is entering into the system, into the neutral species, and we are getting an anion. It is an exothermic process because energy is liberated. The more negative the electron affinity value, the higher an atom's affinity for electrons. So when we are getting higher and higher electron affinity, that means more energy we are getting in the surrounding. That means the higher an atom's affinity for electrons. It is having more affinity for electron. The energy is released when an electron is being added to a neutral atom. Thus, first electron affinities are always negative, whereas second electron affinity is positive. Now, what is the reason? For example, let's see the case of halogen fluorine. Now in this case it is having configuration as 2s2 2p6. So 2p5, it is having configuration as 2s2 2p5. That means it only needs one extra electron to attain this noble gas configuration. When we are adding that electron, some amount of energy is liberated because it is having very high affinity for electron. It will gain that electron and it will attain the noble gas configuration. The configuration it will attain is 2s2 2p6. So it is very stable configuration. Now it is already stabilized. If we want to, now we have got the anion, that is fluoride negative. If we want to add one more electron in this case and we want to have the species like F2 minus, in that case we are going to have the configuration as 2s2 2p6 3s1. That means whole new shell has to be added, and we are changing the noble gas configuration, which is not is very recommendable. So basically when we are already having an ion in this case, it is very difficult for us to add one more electron, especially in this specific case. So this energy is, we are getting some amount of energy, this is negative energy, but over here we have to provide energy so that one extra electron is adding into one new orbital. The electron affinity of an element is a measure of that element's tendency to act as oxidizing agent, electron acceptor. In redox reaction, we know there are oxidizing agent and reducing agent. Oxidizing agent are those which can easily accept electron. Reducing agent are those which can remove electron from the system. So when electron affinity value is great, that means those compounds or those elements can be easily used as an oxidizing agent in different redox reaction. And is generally related to the nature of chemical bonds the elements forms with other elements. So it is very important whether it can accept those electrons. For example, if I will see the molecule as sodium fluoride. Now we know that sodium has a tendency that it can remove that electron and it can have the cation species, and fluoride can easily accept that electron and it can form the anion. So we can know what types of bonds are formed when we are considering species like this and when we are considering electron affinity of different species. Next, if we see the values also, electron affinity increases from going left to right, we have discussed, and because of the increased nuclear attraction, and when we are moving from top to bottom in the group, the values gets increased. For example, this is our values: lithium, sodium, potassium, rubidium, cesium. The values are getting decreased and the less amount of energy is getting liberated when we are coming from top to bottom. Similarly, in this case also, fluorine, chlorine, bromine, iron. And if we compare these two values, because over here we are having the alkali metal configuration which is already having one electron. If you want to have an extra electron, in that case very less amount of energy is liberated. But if we are considering the case of halogens, because it is having configuration as p5, and when we are adding one more electron, then it will attain the configuration of p6, which is the stable noble gas configuration. In that case very high amount of energy is liberated. This ends our first part where we have considered the three properties, periodic properties: atomic and ionic sizes, ionization energy, and electron affinity. In the coming second part, we will be discussing some more properties like electronegativity, polarizability, and so on. So I'll see you in the second part. And if you want to read more about this topic, then you can refer to the book by Electron Publishing. The link of the ebook is given in the description box below. Please like, share, and subscribe to these videos. Thank you so much.
All rights reserved. This video has been prepared for educational purposes only. No part of it may be reproduced or copied without the permission of the copyright holder.